Okay, recording. All right, so we got a question here. Since we're looking at a product, going back to reactants, should the new I in reverse result in a change in sign? That's a good question. I do think the extent should be always positive, and yet this example is coming out with a negative. All right, we'll put that in the bin. We've got a lot of things in the bin, but we'll put it in the bin. All right, let's carry on now. I've given you some, I gave you these slides, right? And there's a lot of blank ones. And why do I give you blank ones? Because when I know that I'm going to kind of develop some equations, there's some places for you to put them. And I think I said this before. Obviously, the text walks you down through the development where some of these really useful equations are coming from. And I think the process we're going through right now, obviously you've come through Gen Chem and you know what equilibrium constants are and how to use equilibrium constants. But in Gen Chem, we don't, or in the principles I call Gen Chem, what we don't go into is where does that come from? Where does that concept of an equilibrium constant come from? And so that's what we're moving through in this chapter. And we're going to move through it because we're going to start with a limited situation of talking about gases and pressures and that sort of thing, and develop this move towards the development of an equilibrium constant. And then we're going to expand it to solids and liquids and ions in solution. All right, so we're in this kind of limited scope arena right now, working through these fundamental equations to see where do we get to, and then we'll broaden that definition and show where it can broaden pretty nicely, because solids and liquids don't contribute to this a whole lot, and ions can be handled in a certain way, and so then the definition becomes broader, much broader than just gases. But for right now, we're kind of talking about gases. So again, starting here with extent, we have the extent is equal to the Ni minus Ni0 over this coefficient. Now, if we look at on an infinitesimal change basis, if we have many small incremental changes in the moles, it's going to be equal to it can be equal to this equal to the new I, the coefficients from the equation, times the infinitesimal change in the extent of the reaction. And if we go to dg, we went back to our fundamental equation. This, I should have put the equation number down here, but this is the equation we had from chapter 4. This is this fundamental chemical equilibrium equation. The dg is equal to n minus sdt plus vdp plus the sum of the chemical activities of each species times the change in that species. All right, now right above it we have an expression for dni And if we limit this to constant temperature and pressure, you limit this to constant temperature and pressure, that all falls out of there. And we substitute this for dNi, we get that this equals and if you were Greek, you would love this. There's enough of the Greek language right there. Now, no, there's no I after this because, remember, we just looked at it. Doesn't matter which species you look at, you get the same extent of reaction. So then, if you divide both sides of this equation by the change in the extent of the reaction, you get that delta G over the partial of the extent at constant temperature and pressure is equal to this sum. And this now is becoming really your delta G of reaction. At any particular extent of the reaction, you're basically looking at the change in the free energy of that reaction at that point in time. And for equilibrium, the change in the free energy of the reaction is zero at equilibrium. It's moving back and forth. It's a dynamic equilibrium, moving back and forth between reactants and products. The delta G would be zero, which means that's going to correspond to this term equaling zero. All right, so that let's take a look now at this equation here, where we got to here. The delta G reaction for equilibrium, at equilibrium, is that the sum of the chemical potentials times the coefficients of the reactions is going to be equal to zero. All right, so a simple reaction in gas phase. We've got this reaction. A's is converting to B's. So just a general reaction. And the delta G of reaction is going to equal the sum of the mu i's times the nu i's. So that's going to equal B times the chemical potential of B minus A times the chemical potential of A. Okay, why minus? We've got a sum here, mu I times nu I, sum, and I got B, mu B minus A, mu A. A is a, pardon me, there's an uppercase and lowercase a. Uppercase A is a reactant, all right? So that nu I, we're making a sum here, but that nu I is actually minus 1. Or it's minus a. It's not minus 1.
The lowercase a and b are the coefficients.
Yeah, those are the coefficients. This is the coefficient in this reaction.
Sorry.
Yeah, so that's what that is. So this is nu A, and it is negative because it's a reactant. Okay? So now, let's assume, for the time being, assume ideal behavior. We're doing this in the gas phase. So if it's behaving ideally, this mu is going to equal the mu at standard conditions plus RT times the log of P over P naught. And this, we got this far Wednesday. We were into this equation Wednesday, developing this. Looking at the change in the Gibbs free energy of a reaction, final minus initial, change in the chemical potential, final minus initial. We got to this kind of an equation. So the change in the chemical, Gibbs free energy of the chemical reaction is going to be equal to we're going to have a term like this for B, and we're going to have a term for B, and we're going to have a term like this for A, and we're going to have products minus reactants. So we're going to have B times the chemical potential of B at standard conditions okay, so this is going to represent B. You with me? So the overall chemical potential here is the chemical potential at standard conditions plus RT times the log of the pressure of B divided by standard pressure, 1 atmosphere, if we're in atmospheres, or 1.01 bars, etc. Okay, minus A times the same term for A. This is the chemical potential of anything, and we've got two things here: our product minus our reactant. And remember, when we do these, we always bring in the coefficients. When we do a products minus reactants kind of equation, we're multiplying by the coefficients. Okay, where does that get us to? You can, if you took away these parentheses, you'd have this minus this plus that. Okay, so I mean we're not multiplying anything here, we're just adding and subtracting. Yeah, so we get to this. It's going to be the log of PB over P naught minus the log of PA over P naught. And this term here can result in just taking this divided by this, the ln of PB over P naught divided by PA over P naught. And have an RT in front of it. And this term converts into just the delta G of the reaction at standard conditions. So the delta G of our reaction at whatever conditions the reaction are is going to equal the delta G. Now this isn't a delta G of formation. This is a delta G of the reaction at standard at 25 degrees C and 1 atmosphere, plus RT times log of these things, what the pressures would have been at this condition, but divided into the pressure of this reaction.
Those pressures cancel out.
The P knots.
The P knots cancel out. So it's just PV over PA.
Wait a minute here. Did I leave out the yeah, I did leave out these. Well, right. They do in this case because, well, maybe they don't in this case because we do have coefficients A and B. Yeah, I oversimplified this. This is this to the power of A.
Where does the power of A come from?
Or this is that's the power of B.
Because it wasn't there when you were driving it earlier, and now it just shows up.
Well, we multiplied it by A earlier, and then we kind of missed it, the intermediate one.
That doesn't explain how the natural log, or if it's multiplied in there.
I think right here.
There, yeah.
It's a log rule.
Yeah,
So
it's
you
right
can do
there.
that, but
That's right.
It's like algebra.
That's right, because we do have this times this. Yeah. So I missed that. I missed that right in here.
We put it, just around there.
And this is going to be to the power of B, and this is going to be the power of A. Okay, yeah. Otherwise, Grant, you're right. Those would have crossed out.
Yeah.
But we got that power in there. Okay, now this whole thing is going to be given a new term, Q. The reaction quotient. Okay, so that's going to be given reaction quotient, and simplify this a little bit more to this. And we only had, in this particular example right here, we only had one reactant going to one product. Let's try to think of an example. And I think in your homework, or maybe even in chapter 4 homework, you had the reaction NO2 going to form N2O4. So there's an example where you have a reactant producing, one reactant producing one product. So 2 NO2s produces 1 N2O4. So that would be kind of comparable to this example right here. simple, only one reactant, one product. But if we want to look at, just kind of expand this to any number of reactants and products, you can change it to this. Now, does anybody know what capital pi? Okay, mathematically, it's pi over p naught, and it's going to be to the absolute value of the power is going to be to the absolute value of the coefficient of I.
Okay.
And
So pi is that?
well, that's not pi. That's a mathematical, I don't know what you'd call it, a mathematical operator that's basically saying we're not going to sum these terms, we're going to multiply these terms.
Okay.
We're going to multiply. If there's two i's, we're going to get that term for each one of them and multiply them together. And likewise, we're going to do that with the reactants. I'm not sure what that is called, but that's the operation. You're going to take all these different terms and multiply them by one another. So this is going to be
Like
J.
sum, but
Yeah, it's not the sum, it's product.
yeah.
It's the successive product of all those terms.
But there's multiple terms. Yeah.
Right, so this is going to be PJs. And we're using the absolute values. I think we can use these absolute values because we're more or less already taken into terms the sign that it's a reactant or a product in the derivation of this equation. To really get this down here, it's already been, the negative sign of the reactant has already come into play. Follow me? So now we're using just the absolute value of those coefficients in this equation. Okay. Okay. Where did that get us to? Did that get us anywhere? Let's see. Where am I? All right, we're running out of time, but let's just look at this real quickly. This is kind of, all right, what do you do with this complicated, this reaction quotient? Here's a reaction, hydrogen plus oxygen going to water. You do have two reactants, one product, all gases. Here's the pressures of these. And to calculate the chemical, first to calculate the Q, so Q is up here, equal to all this. Crunch this out real quickly. You got about a minute. See if you can crunch that out. What do we have here? We got the pressure. Here's the product, water. Just take standard pressure as 1 bar, and it's giving it's not exactly 1 bar, but take it as 1 bar. Simplify that calculation a little bit. And these exponents are the coefficients in the balanced chemical reaction.
Maybe I did it wrong. Oh yeah, I squared it. I squared it.
You don't want
Bottom.
to
Yeah.
Yeah. Mad.
Well, you guys did that fast.
Well, you can ignore most of it. You can ignore all the 1 bars. So then it just simplifies down to 0.556 squared divided by 0.775 squared times 2.8.
Okay. So then, so what are you getting? You got 0.178?
Yep.
Okay, 0.179, sounds fine. And then using equation 5.7, you've got, so this is the delta G naught, this is the delta G at standard conditions of the reaction, of that reaction that's given right there, times R T times the log of Q, and this is joules, this is joules, so we're just converting the joules to kilojoules to match it up with this. All right, so that's your example 5.4. That takes you to page 125. All right, and Q is getting close now to K. We just have to make a few more limitations on it, and we'll be starting to talk about an equilibrium constant. We're not quite there yet, but we're close to it through all of that. Oh, here you go. By special request, Liz.
Yes, thank you. It's not due till next Friday though, right?
Yeah, I don't know when this is due. Probably
After
next
break.
Friday. Okay, and I haven't done all of these yet. I'm going to do some of these, and if I crunch through some of these and say, boy, I don't know it. We might cross 1 or 2 of these out of here.
Oh.
Sweet. So don't spend too much time.
Yeah, if you get into one that really doesn't look straightforward, then talk to me about it Monday or Wednesday, and we might drop it.
So did you get, when you talked to Dr. Crane about that problem, 4.8?